हम लोग आज एक काम करते हैं. लेट अस डिस्कस समथिंग. So I'll talk about something called something called let us discuss classical mechanics in one dimension. Huh? Just a minute. एक काम नहीं कर रहा है, सब हैंग हो गया है. Just a minute. गड़बड़ हो गया. Okay, so let us discuss classical mechanics in one dimension. Huh? Let us discuss classical mechanics. Suppose you considered motion of a particle in one dimension. Say x is the dimension. Okay. So this particle is subjected to some potential which is called potential Vx, and this particle has a mass. Okay. So this particle m is the mass of the particle. So there is a particle which is moving in one dimension, and m is the mass of the particle, and so since this particle is in a potential Vx, this would correspond to some force acting on the particle. ठीक है. तो कोई भी पार्टिकल अगर एक फोर्स एक पोटेंशियल बैरियर में या पोटेंशियल फील्ड में मूव कर रहा है, that means that the particle is acted upon by a force. For simplicity, we will consider just one dimension where x is the dimension. In Cartesian coordinate, you can consider this as a coordinate in Cartesian coordinate. So therefore x is x as a function of time. Okay, so this position x we think of as a function of time. So can anyone tell me an example of a potential Vx in one dimension जो तुम लोग पढ़ के आए हो? So let us discuss classical mechanics in one dimension. Let us discuss classical mechanics in one dimension. So suppose you consider motion of a particle in one dimension. Say x is the dimension. Okay, so this position x we think of as a function of time. So can anyone tell me an example of a potential Vx in one dimension जो तुम लोग पढ़ के आए हो? कोई एक पोटेंशियल ऐसे बोल सकते हो कि जिसका एग्जांपल तुम लोगों को पता है?
ग्रेविटेशनल पोटेंशियल तो पढ़ी है।
No, just in one dimension. Very simple, classical mechanics. Every one of you have gone through this kind of example.
The spring force.
Yes, the spring force, the simplest one, just the spring force. So where Vx is just the simple harmonic potential, right? So an example है इसका for an example, is just simple example. The Vx is half kx square. So which is a simple harmonic potential. This is a simple harmonic oscillator that all of you are familiar. By the way, can you read my handwriting? It's not very good, but can you just manage to read it?
Yes, sir, we can manage.
क्योंकि मेरा जो व्हाइट बोर्ड था जो मैं यूज करता था अब तक वो खराब हो गया है. This is a new one and I'm not quite familiar to it. Anyway, so this means that when what does this mean? So this means that when the particle is say at x equals to 0 position, then the potential is 0, which means that there is no force. The particle feels no force. Potential goes to 0. Okay, and when x becomes large, then the potential becomes large and the particle feels force, and the force also becomes large. Okay, that means the particle motion will stop at some point because the force is becoming large with x, and that gives rise to what we call the simple harmonic motion, because at x equals to 0 it feels no force, so the entire energy is the kinetic energy and it moves like a free particle near x equals to 0, and as x increases, as x increases, f increases, so which means that the particle feels more and more force and then motion stops and the kinetic energy becomes 0 at the end points of the oscillation, and then it entire energy is the potential energy. This is what it does. Now these dynamics we understand through Newton's law. So these dynamics we understand through Newton's law, which tells that m d2x dt square is the force, the external force that is acting on the particle. So, and this tells us the entire dynamics of the system, because we can solve x as a function of time, and we know that for this kind of potential this is a sine function or a cos function or a combination of sine function and a cos function. Okay, so both solves this equation, and this solves the problem, the dynamics for this particular problem, but this is a one-dimensional problem. So if we plot x as a function of time, we can figure out some sinusoidal motion for this particle. Now the question that one can ask here, that how do we make sense of this equation? ये जो न्यूटोनियन इक्वेशन है तो of classical mechanics, how does that make sense? Can, in other words, this one can ask that can we can we derive this from some underlying principle? Can you derive this from some underlying principle? तो हम लोग ये क्वेश्चन कर रहे हैं कि that the Newton's Newtonian mechanics, the classical mechanics that all of us familiar, where from this comes? ये जो second order differential equation है, इसको solve करके we solve the dynamics. Basically it tells about the entire universe itself. Even the complicated planetary motions can be explained this simple principle. So can we understand this equation from some basic principle? That is the question, and this question we want to address today. Okay, this is the question that we want to address, that the Newtonian mechanics, simple Newtonian mechanics, can it be understood from some very basic principle of nature, which tells us that such a dynamics is allowed, such as dynamics is, because this तुम लोग जब न्यूटन्स इक्वेशंस पढ़े हो, it must be come as a surprise to you that where from this equation comes, because this cannot be derived. Okay, so Newton's laws of motion, this cannot be derived. It is a second order differential equation. It's very strange why this has to be true. It's a mystery. Okay, we cannot derive it. So we'll try to shed some light on this question today, and we want to understand that if there are some basic principles that can actually lead to such dynamics. This is the statement of the problem. If any question regarding the statement of the problem, please ask me. I can explain it more. Is it clear? The question is clear to all of you?
Yes, sir.
Yes, sir.
Yes, so remember the basic principles of physics. This cannot be derived. We start from some principle and we derive it, we build up a theory, and then we match with the experiment. And if it matches with the experiment, we say that this is the law of nature, this is the dynamics of the system, this is how it is working. But we don't know exactly why this dynamics has to be true, why this law has to be true, but we can just experience, from experience we see that okay, this is true. Okay, so this is a deep fundamental question, but we'll try to understand this from a slightly different perspective today. Okay, so let us understand this question from slightly different perspective. So people have thought about it for a long time, that is there any a more fundamental entity is lying behind this Newtonian mechanics. Even not only Newtonian mechanics, actually it turns out to be the most the fundamental principle that governs the entire world, the entire universe, all the motion, starting from subatomic particles to the entire universe. So then we let us build up a more fundamental principle. Okay, so this principle is called principle of least action. Now, principle of least action, it tells you, so to start with, we define a quantity. Let us build up a theory, and then we'll see that Newtonian mechanics is coming out. How it is coming out, that we will see. So we define a quantity, which is an integral of L dt. Now I am not now let me define what are these quantities. So L is a function of position, velocity, and it's a function of time. Okay, so this quantity L under the integral we call Lagrangian. This is a quantity which we call Lagrangian, and this quantity on the left, this quantity we call an action. It has a name, it's called action. This is a one-dimensional problem. So Lagrangian is a function of x, x dot, and time, and this is integrated over some time ti to tf. So the particle we are integrating from some initial time to some final time. Now the principle of least action, it says that this is a principle. Okay, so it says that the action when del s del x when evaluated for the classical trajectory or the classical path of the particle, then this should be 0. That means this quantity is extremum, so it has to be either maximum or minimum, but some it has to be an extremum. So now what is this? What does this mean? This means that if you think of, so this function L we have not yet specified, but for a given system there is some function, say L, and L is a function. So this is say Ti and this is a Tf. So this is, I am plotting this this L for different time for so this is Ti and Tf, and this, suppose here we plot L along y-axis. Now L being a function of x dot and time, and x itself is a function of time. Remember that x which is a position, so x is a function of time, and x dot, which is a velocity, this is also a function of time. Okay, so x and x dot, they both are function of time. So this means that this L that we have defined here is also a function of time. So if you know this x and x dot as a function of time, then you know this quantity L, and this means that for different trajectory you will have some different curve like this between starting from initial time to final time, and this will corresponds to different trajectory between initial time and final time, right? L will be different for different path. Is that clear to all of you?
Yes, sir.
Yes, sir.
Because x is a function of time, x dot is a function of time, and L sometimes explicitly is a function of time. So for different trajectory, okay, L will be different because x is a different, and L will be different, and then you can think of a different path between time Ti to Tf, which corresponds to different trajectories between initial time to final time. So this you can also think of, instead of L, you can think of just So like you can think of L, you can also think of this as X or X itself. So different trajectory, different value of L. That means this quantity, this S, whatever I have called action, this quantity is now, it is just a function of path. For different path, this is different. So this is a function of path. So this quantity action is different for different path, because for different path there are different trajectories, and this quantity L is different for different paths. So the integral, the value, this number will be different for different paths. So this is basically, it's a function of path. So this quantity action which we define here, this quantity is sometimes is called, it has a name, it's called functional. So this is basically, it's a function of path. So we write it as a function of xt. So this quantity action which we define, it is a function of the path or the trajectory between the end point and the final point. Okay. Now this is the background which we need to understand the principle of least action. It tells that this number LDT, integrated from initial time to final time, this number is extremum for the actual path. There can be many paths, but for the classical trajectory, the classical path that the particle follows, this quantity is maximum. It's called the principle of least action. Okay, so is up to this point, it is clear to all of you?
Yes, sir.
So
Yes,
this is called principle. We cannot derive this, but we propose this. Let us see whether this gives us the correct dynamics. Okay.
Excuse me, sir.
Bolo.
Sir, please tell what is the classical path again?
The classical path is that path for which this action is extremum. We don't know, but we'll impose this condition and we'll see that we'll recover Newtonian dynamics, because Newtonian dynamics gives us the solution x as a function of time only for the path of a classical particle, or the classical, for example, a simple harmonic motion. The particle has a definite trajectory. It satisfies Newton's equation. The particle which satisfies Newton's law is a classical particle, and the trajectory that we obtain by solving Newton's law is classical trajectory. Is that clear?
Yes, sir.
So by classical path I mean x as a function of time which you obtain by solving Newton's law, Newton's equation. So in other words, this extremum condition should reproduce Newtonian mechanics, Newton's equation, because that then only it is compatible with the statement that it is a classical path. So we have to now see how this is coming. Okay, now comes the hardest part, and the hardest so the challenge comes now, how to implement this principle of least action. If you want to implement this principle of least action, then you have to make a wild guess, and that guess is, what is this Lagrangian, what is this quantity that will give us the correct dynamics or the Newton's equation. So let us see. So one has to make a wild guess of the Lagrangian. Unfortunately, there is no prescription to write down the Lagrangian. There is no prescription that you can follow to write down the Lagrangian other than just looking at the symmetry of the system. Okay, now here we have to make a wild guess. So the guess, so to write down the Lagrangian, one has to make a guess. So guess what should be L at del x should give us the Newton's law. Okay, now this is very simple. This is the simplest case. So the Lagrangian here one writes down as half m x dot square minus v of x. Suppose someone says, okay, let us propose that the Lagrangian is something kinetic energy and a combination of potential energy. It's a guess. So that we will recover Newtonian mechanics following this principle of least action. Okay, suppose someone says, so you write down the action. So you write down the action. So this is a function of path, and you write down the action now with the Lagrangian. So half m x dot square minus v x. Now we have to consider a variation of this quantity with some boundary condition. Now what are the boundary conditions? Now we have to consider a variation with the boundary condition. So we have to impose the boundary condition Remember, this looks very non-trivial and intuitive, and this principle governs the entire physical world. Because whenever we want to build up any theory, even standard model, it comes with a action principle and a Lagrangian formulation, and then the entire theory of general relativity or standard model or quantum field theory is based on this very simple principle, yet very non-trivial actually. So we're trying to understand this from taking a very simple example of particle in one dimension, motion of a particle in one dimension. Now we have to impose boundary condition. You have to impose a boundary condition. Now this boundary condition that one impose is the following. So we impose that delta x at initial time is 0 and delta x at final time is also 0. That means these endpoints of the trajectory, here there are no variations one can consider. So all the paths that vary, they vary between these 2 points. So this point and this point, these 2 points are kept fixed, where we do not consider any fluctuation. There are no fluctuation at the end point. So the x that can fluctuate is between these 2 endpoints, but at the end point these fluctuations vanish. This means the vanishing fluctuation at the end point. Okay, this means the fluctuations, they vanish at the end point. So fluctuations vanish at endpoints. Okay, so this is the boundary condition, and when we will take the variation of delta S, we will see that this boundary condition, when imposed, then principle of least action recovers, or it finds out the Newtonian mechanics that we are looking for. Okay. Okay, so if any question you can ask me. If not, then I can now tell you a little bit of mathematics, how to obtain this, and
Sir,
bolo. Any question?
sir, why only we are using least action? We could have used least time also.
Time is a parameter. So time is flowing from Ti to Tf, but what changes between Ti and Tf is something called the S or the Lagrangian, right? Because this is a different for different path. Time is fixed. Time is moving from initial time to final time. Okay, you start taking your clock. After 10 seconds, you measure S for different path, and you will see there are a set of numbers are coming. Now, out of these numbers, you want to find out which number will correspond to the actual path of the particle. Not all numbers are valid or real numbers. Okay.
Yes, sir. So, why isn't anything like principle of least time?
Oh, principle of least time. That's a principle of least time. It's something is it's a different thing. So principle of least time means that between 2 points, only that path is. So if that's the least trajectory, the least path, so the time would also be least, right? If the velocity is something is moving with some velocity, and if that covers the minimum distance, the minimum path, then naturally the time would also be the least, right?
Sir, but
But
if
here we
there
are
are
trying
other
to
parameters,
what we are
like
trying
for
to understand.
example,
No, the point is that here we want to recover Newtonian mechanics from some principle, and we are building the theory according to that. We know where we want to land up from a different perspective. इस problem को समझो. पहले the first thing is that we know what we want. To reach there, we have to develop a theory so that fits what we need actually, not the other way around. We cannot randomly consider a variation. We are proposing something and we will see that this variation will give us what we need actually. Is that clear?
okay, sir.
मतलब इसका मतलब यह है कि हमें क्या चाहिए वो हमें पहले पता है, हमें ये पता है कि हमें कहाँ रीच करना है. फॉर दैट हम लोग थ्योरी डेवलप कर रहे हैं. वी आर डेवलपिंग समथिंग टू अंडरस्टैंड दैट इफ इट कैन बी अंडरस्टूड इन अ डिफरेंट वे. Because when Newtonian law we write down, we don't know where from it comes. That is the puzzle. We don't know. So that's why we're trying to understand it from a different point of view. Okay, so for that, this is the theory, what I am saying. ये claim है. Now let us check that this claim is true. Okay, so let us. और किसी का कोई question है? Any question? Ask me, don't shy. You can ask me whatever you have in mind. So please ask me more questions. Okay, so let us consider the variation now. So time goes to Ti to Tf. We have half m. Delta will hit on dx dt square minus we have dv dx delta x. Okay, this first step is clear to everybody?
Yes, sir.
सबको clear है? Everyone is happy?
Yes, sir. Happy, sir.
Okay, fine. So this is the first thing we are doing. Now ये जो टर्म है, इस टर्म को हम कैसे लिख सकते हैं? दिस टर्म डेल्टा ऑफ dx dt होल स्क्वायर. So delta of dx dt whole square, this will be 2 dx dt delta of dx dt. ठीक है? Okay?
Yes, sir.
Okay, so this means that now you have to use a simple identity this I give you as a homework to check that delta of dx dt, just from the principle of differentiation, you can show that delta of dx dt is ddt of delta x. This is simple proof. We just check at home from principle of differentiation that this identity holds. Okay, so this identity, if I use here in this expression, then delta and dt operator, they just reverse. So this becomes let me write it. So this becomes ddt of delta x. So delta and d, this operation commutes, in other words. Okay, delta and d, they commute. Okay, so if this is clear, then we just substitute it in this case here. So let us just substitute. Is it okay or I am going fast? Speed ठीक है तुम लोगों के लिए? Is that okay?
Yes, sir.
So
Yes.
this, first of all, one thing is that these two we remove, we get rid of this two, this half factor here, because there is a 2 factor here. So we get rid of this half factor. So this becomes m dx dt ddt of delta x. So now we will do the partial integration of the first term. So what this gives us, the partial integration of the first term. Let us see. हाँ बोलो.
Sir, how did we came to the expression of that dx by dt whole square equal to 2 dx dt d del x, the last expression?
This expression, oh, this delta variation.
Yes, yes, yes.
So this is something like you are just differentiating something with respect to dx dt, and then this is ddt of delta of dx dt, right? This is a function delta of f square. What is delta of f square? Twice f delta f, right? It's not get so it's something similar to this. So any function, if you have, so you have delta of some function of square, then this is twice f delta f, right? This is the identity of differential calculus. You know all this identity. I hope this is known to all of you.
Okay, okay. Thank you, sir.
Yes? Sure? ये सबको पता है तो?
Yes, sir.
Okay, because I'll assume some basic that you know actually. Now m dx dt ddt of delta x, this you write ti to tf ddt of m dx dt delta x minus m d2x dt square delta x. Is that step clear?
Yes, sir.
Yes, sir.
सबको क्लियर है? Okay.
Yes, sir.
Now what is the first term? This total differentiation. ये पहला टर्म का वैल्यू क्या है? कोई बता सकता है? फ्रॉम द बाउंड्री कंडीशन. Okay, so let me write it down. This is equals to m dx dt delta x ei to tf minus m d2x dt square delta x dt. अब बता सकते हो पहला टर्म का वैल्यू क्या है?
0.
0 है. Very good. Because delta x from the boundary condition we have imposed that the variation is 0 at end points at ti and tm. So this total this total derivative term, which is this term, goes to 0 because of the boundary condition, because the end points are fixed. There are no fluctuations at the end point. This point is clear to all of you. That please let me know if this is clear to all of you.
Yes, sir, it is clear.
सबको समझ में आया क्यों पहला टर्म 0 है? Because delta x, the fluctuation vanishes at the end point. So the first term is 0. So we are finally left with this expression. So let me just put it here. So this becomes minus m d2x dt square, and this delta x I can take overall outside. So I put a bracket here, and this becomes the integration. Okay, is that clear? So now we apply principle of least action. So if you are familiar with Taylor expansion, are you familiar with Taylor expansion?
Yes, sir.
Taylor expansion of a function.
Yes,
So,
sir.
so from the Taylor expansion, this term you identify as del s del x, right? This is like you are expanding a function s. So this is like you are expanding a function x, which is a function of some classical path, say, plus you have del s del x at x equals to x classical path delta x plus dot dot dot. So if I claim that this is the classical path and this action is expanded about the classical path, so this is my delta s then, which means this term, the first correction to s about s classical. Is that clear? So this means you are just taking a variation about some classical path, an infinitesimal variation, and this is a Taylor expansion of the function for the infinitesimal variation. Does that make sense?
Sir, can you please go through this step once again?
Which step?
So the Taylor expansion.
So s is a function of path, right? So x means path. A particular x means one particular path from initial time to final time. So let me draw here. So this means one particular x means one particular trajectory between initial time to final time. Okay? Now I consider a small fluctuation of this path from the classical path. Suppose this was the first path was the classical path, and then I consider a small fluctuation about the classical path between the same time interval ti and tf. So this corresponds to the change in the action for that small variation. The first term here corresponds to the change. It's something like this. If you expand a function fx about x equals to x naught, then first term is f equals to x naught, then del f del x delta x plus higher order terms. This is precisely the same thing, but here the variation is over the path. Now tell me if this is clear.
Yes, sir, it's clear.
This is the calculus of functionals. This quantities, this action is called the functional. This is just a differential calculus for the functional. Okay. So the first term is basically the delta s, which is a variation due to the deviation from the actual classical path. So now if this is the principle, so if we impose the principle of least action, then this quantity in the bracket, this has to be 0. This quantity has to be 0. This quantity in the bracket. So using this, so this uh, uh, so let me write it properly. This quantity is 0. So which means that this is 0 and This is precisely the term in the bracket is 0. So this means that m into x t square is equals to minus dv dx. But minus dv dx, what do you know as force? This is a conservative force. If potential is a function of x only, then the force field is conservative. So this is what we identify as Newtonian mechanics. So Newtonian mechanics, we understand that the Newton's law can be derived, rather, quote unquote, from some underlying principle which is called the principle of least action. This is a very simple example, the simplest of the examples where you can test this principle of least action to derive the Newtonian mechanics. Okay, so now we stop today. If you have any question, ask me. If this was clear to all of you, you have learned something new, then just uh, let me know, or any question you can ask me. So there is a, bolo.
Sir, I want to ask, what's your actual research field?
Oh, I work in string theory. So my research is deals with string theory and quantum field theory correspondence.
Okay, sir.
Any other question that you want to ask? So I just want to refer a book by Landau. This book is one of the classics. If you are interested to learn classical mechanics and mechanics in itself, then this book, Landau's Mechanics, will be useful. Those who are interested, you can take a look at Landau's Mechanics. There is a whole series of Landau Lipschitz you can buy if you're interested in physics. So that's it. Any question? Any other question?
So, sir, this Lagrangians that you use, they are like generalized versions of Newton's law.
So Lagrangian is a way to understand the dynamics of a system. In some sense, yes, it is. It is a more general principle or a more general prescription that gives you the Newtonian mechanics, understanding of Newtonian mechanics from some basic principle, and Lagrangian is the key element for that. But as I mentioned, that you have to take a guess what the Lagrangian should be that will produce the correct dynamics, because there are complicated systems for which it is very difficult to write down Lagrangian. It's very difficult. Sometimes symmetries of the problem help us to write down the Lagrangian. But if you have a very complicated system, you don't know what is the Newtonian version of the dynamics for that system. It is completely impossible to write down without this action principle of least action. That is why this is appreciated all over the discipline.
And sir, we derived this for one dimension. So, yeah, how more generalized we can be in this derivation?
So then this x you replace by a general vector, position vector r. Okay, so this equation will become something like this. Okay. So if you want to generalize this, then you can think of something like this. Let me write down and then I'll. So this was the simplest case, but
Sir, like a
For
general
more
case,
general case,
saying that
you just replace x by position vector r, which is a function of x, y, z in 3 dimension, and you write down the Lagrangian as L dt, where L is a function of r dot, and time, and this keeps what you call action, and you apply the principle of least action. So this will give you the same calculation, the same way. What will give you this equation? You will get m d2r dt square minus grad v. So this grad is the gradient operator that you know from your calculus, differential vector calculus.
sir, we don't know vector calculus till now.
Mm-hmm.
We don't know vector calculus.
Oh, the vector calculus is okay. So then this you will understand when you learn vector calculus. So grad is something like a differential operator, which also acts like a vector. In 3 dimension, it has 3 components. So this is the course of differential vector calculus. So this grad is this operator. So x component, y component, and z component. It's a Cartesian coordinate. There are 3 unit vectors, and there are 3 components. So and then this grad, it has 3 components. So grad v is the 3-dimensional version of the force that I have written. Okay, and r is the position vector, which is x plus. So r you know, right? The position vector in 3 dimension. This perhaps you are familiar with.
Yes, sir.
So this is x plus y plus z. This is the position vector in 3 dimension, and this is the grad operator in 3 dimension. So since you asked the general version in 3 dimension, this will be the general version in 3 dimension. Any other question?
Sir, this del S by del X is equal to 0 is specific to Newton's. Like for Lagrangian and Hamiltonian, this changes or what, sir?
No, see, Newtonian mechanics is a very limited case of some complicated system. It's a very simple case. In practical situation, suppose you are dealing with very complicated system, quarks, leptons, or any other fields, then this Newtonian, there is no meaning of writing a Newton's motion for that. Then we start with this action principle. We have to find out the Lagrangian, and then we have to find out the dynamics of the system from that Lagrangian. So this is the most general prescription to write any complicated dynamics, any complicated system, starting from subatomic systems to a classical world. So this is the most general framework. Okay,
Sir,
I just try
my
to convey
question was,
that.
sir, this del S by del X is equal to 0. Is it true only for Newtonian mechanics, or is it true for the other forms of mechanics like
Any classical system, any dynamical system, be it classical or quantum, this is true for any dynamical system.
Okay, sir.
It's not just. So this I explained using the Newton's law and in simplest case of 1 dimension, but this is applicable in any to any system. Okay, so if you want to learn more on this, then bolo.
Sir,
Any
please can
any
you give
question?
a quick summary so that we remember the take back of what is done here for the Newton?
Quick summary of what?
Sir, what the whole process?
I just did it. So it just ask your friend. I mean, you want me to write down everything from the beginning?
No, sir, just one last summary if you could give so we remember the takeaway from this.
So it's nothing more than what I have said, but as you have requested, let me just write a few lines for that and then I stop. So you define an action, which is, this is just for this classical mechanics problem, okay? For complicated system, this will be different, but the basic structure is same. So you define an action, which is a function of path. So in one dimension, what we have seen, that you define a quantity which is called Lagrangian, and you call this quantity action, and remember this whole entity is dimensionless. This whole quantity is dimensionless. The action is a number. And then we say that we impose a principle which we call the principle of least action. Where we call that this number will be least. Okay, so this is called principle of least action, or it's called the principle. So this number, this x, which is a dimensionless quantity, it's a number. This will be extremum for the classical path. That means for the classical path, if you take a variation about the classical path, then this will be 0. Okay. So you can think of this as a Taylor expansion, where x is any path, and you take an expansion about the classical path like you do in any expansion of a function. This is like a Taylor expansion about the classical path. Okay. This is delta x plus, this is very small, delta x is very small. This is like expansion, like a Taylor expansion of a functional. So this is called the Taylor expansion of a functional. Taylor expansion of a functional. It has a name, it's called functional because it is a function of path, different path between the same time interval. So it's called a functional. So this functional, when it's about the classical path, then this is 0. Del x is 0 because then it corresponds to the extremum value, right? Any function, when it is extremum, the derivative of that function goes to 0. This is familiar to you from your calculus course. This is same logic is applied when it's a functional, and this gives you what you call, in this case, the Newtonian mechanics or the Newtonian dynamics. That is what I tried to convey in this class with one example of particle moving in one dimension.
Thank you, sir.
Okay, okay. So that's all about this class. And if one last question anyone want to ask? So thanks for your attendance. Okay, so see you.
Thank you.